Hey, welcome back to another Noria Gear Talk. I am Wes Cash, and I am excited today because we have Drew Troyer here with us, and we're going to be talking about his experience in reliability. We're going to be talking about some concepts that maybe people are quite missing the mark on a little bit. And as always, thank you for subscribing to this. It really helps us out. And Drew, thanks for coming in here.
My pleasure, Wes. Thank you.
Now, part of Gear Talk, right? We are connecting reliable professionals with reliability professionals with reliable information. And we really want people to know who is giving the information. So if you don't mind giving a little bit of background, a little bit of introduction about yourself.
Yeah, sure. So currently I'm the global head of asset management for Anglo American, which is a large multi-mineral mining company. We mine platinum group metals, De Beers diamonds. We have operations, copper operations, iron ore operations, metallurgical coal. So a range of different minerals. We mine in Africa, a little bit in Europe, North America, quite a bit in South America,
okay,
and also in Australia. So we're a large global mining company. About 65,000 people.
So, I mean, very large. So, of course, it's people intensive. It's resource intensive. We got physical assets, scattered all over the place.
We have heavy mobile equipment, trucks, shovels, drills. We have processing equipment for, crushing and conveying and further beneficiation of the minerals. Each mineral is a little bit different. So you treat nickel differently than copper, which is different than iron ore. But yeah. So
mobile equipment, static equipment, you're probably generating your own power, your own steam.
Power generation.
You've got a whole microcosm of all sorts of industries all wrapped into one.
Including renewable power. So we're increasing our footprint in renewable power as a part of our goals to achieve net zero in terms of our carbon footprint.
Well, I think that's fantastic. And of course here, we're talking about reliability. So you've been in the space for a long time. I mean, you've probably forgotten more about a lot of these topics than I'll probably ever know. So I'm honored that you're here, but why don't you give us a snapshot, kind of as you were introduced into the industry, what you've learned as you're going, and now, what are the big things that you're applying now that you thought, man, I don't know why this is still kind of an issue. Why are people still not quite getting this?
Yeah. So I have been around for about 34 years. So I got started in 1990. I was on a project at Oklahoma State, and it was a little company that was developing technologies for performing oil analysis. Oil analysis had been around for a long time.
Sure.
But it was somewhat limited in its application. And what was happening in the 1990s was there was a transition that was occurring, and it was really being led by the U.S. power generation industry. And the transition was to move from traditional time-based maintenance to condition-based maintenance.
Okay.
And because I was part of the teams that were developing these different technologies, which are common now, oil analysis, vibration analysis, thermography.
What we'd call our predictive tools.
Yeah. These were really kind of brand new in terms of being applied for condition-based maintenance. And all of the maintenance that we had done previously, for the most part, was time-based. And I was actually part of a study at what was then called Houston Lighting and Power.
Okay.
And what we discovered was 70% of our reactive maintenance, that's when the machines are broken and we have to fix them, occurred within 30 days following a shutdown where we did time-based maintenance.
So this is a maintenance-induced issue.
Basically, yeah, we would take a perfectly operating pump or forced draft fan or ID fan or whatever, schedule a rebuild on that, and take it apart, put it back together, and break it along the way. So that was a big part of the impetus to move into condition-directed maintenance, where we look for different signs that we we have problems with machines. So we look for the presence of wear particles in oil analysis, or we look for inter-race defects with vibration analysis, or we look for heating electrical circuits, meaning perhaps that those are degraded. That would then trigger maintenance. So not only was the maintenance done when it was needed, but it was more specific. We had this information about what was going wrong so that we were fixing the things that that mattered.
Yeah, and allowed you to have the spare parts that you needed kind of kitted together probably ahead of time, making sure people were scheduled. I mean, that's the biggest thing, right? Reducing the impact of it. I mean, we're judging it along the way. The troubleshooting is done in real time through the whole process.
Absolutely. So, and that does allow us to plan our jobs. Now, a big difference that occurred during this period, we planned our jobs before when our maintenance was time or cycle directed, X hours, X calendar days, or this many tons, or whatever unit we're using to determine when to do a rebuild. But this condition monitoring introduced a dynamic component to the planning and scheduling. So we needed to have enough advance notice so that we could plan and schedule, but we needed to continuously prioritize, which led to the development of different approaches to planning and scheduling. I would say most notably, the greatest influence, my dear friend Doc Palmer, who wrote the book on planning and scheduling.
Yeah, the handbook of planning and scheduling. Right?
Absolutely. So that's the Bible for managing work. So it was really condition monitoring and the movement to condition-based maintenance that precipitated that transition. So I was a part of that group. I won't say that I single-handedly. I was one of many.
Sure.
But I learned a lot, and I was right on the cutting edge of this transition. And then, of course, what we pioneered, basically with a focus on the power generation industry, became then adopted in the pulp and paper industry. Refineries. Refineries were on the leading edge too, the petrochemical industry. But other industries started to adopt and adapt as required these condition monitoring technologies and condition-based maintenance. Then, of course, more technologies came along. The technologies became cheaper. I remember the first thermography camera was nitrogen cooled, and you had to push it around on a cart and everything. And now I can get a camera for a couple $100 that will plug into my iPhone, turn it into a thermography camera. So it's really amazing what's happened with the technology.
So if you're thinking, all right, you're there present, kind of, let's just call it the birth of the universe here as it pertains to condition monitoring, how this pertains into maintenance, predictive analytics, everything. And now you're parlaying that into your role in mining. As you walked into this role, I mean, you're looking across this entire fleet. And I mean, understanding, trying to get your arms around this can be difficult. But you look at them and you say, man, these are still basic things that why aren't we doing X, Y, and Z? What would be those aspects that you feel like people are still missing?
Yeah. So, and there's nothing that I do at Anglo American that I haven't done lots of times before.
Sure.
It's the same. You know, it's still engines, it's still gearboxes, it's still motors, it's still bearings, it's still, electrical circuits.
Are the problems still the same too?
Most of the problems are the same. Okay. Fundamentally the same. And I've got to be honest with you. I was around when the term reliability engineer became somewhat new. Well, it was new. It was not a new term, but it was a new term as it was applied to general industry. And everyone now was becoming a reliability engineer. Okay. And I wasn't quite sure what that was. So this was about 1993. Okay. Maybe 94. This is when people stopped, for whatever reason, being maintenance engineers, and all of a sudden now they're reliability engineers. Okay. wasn't quite sure what it was, so I went to the library, and that's what we did in the pre-Google days. We would go to a library, and I checked out one of these things they call a book. Yeah, it was a book on reliability engineering.
Okay.
And I started thumbing through it, and one thing I knew was I was not a reliability engineer after thumbing through that. So I figure if this is where it's going, if this is where it's headed, I ought to get some skills. So I went to the University of Texas and did a program on reliability engineering, and then later became professionally certified, and still am as a certified reliability engineer. And I can remember at the time, maybe I was young and naive, but I'm thinking, because I'd had these experiences where, we really did move the dial. And it was not always easy. There was cultural resistance.
We've been doing it this way for who knows how long. And
exactly. And we're bringing in what I can recall a manager at Houston Lighting and Power saying squiggly lines, all right, vibration reports.
Oh, okay.
And we were bringing oil analysis reports in which,
numbers on a page, I guess.
Yeah, and oil analysis reports are not particularly user-friendly even now. But back then they were really user-unfriendly. Just looked like it was a chemistry report. And I can remember one of the guys saying we had a problem with one of the lubricants, and I said, "Look, it's I don't know the viscosity. I don't remember the details, but I think the viscosity had dropped from a 320 centistokes. It was like a gear oil on a conveyor.
Okay,
the coal conveyor going up to the crushers, which then go to the pulverizers. So one conveyor fed all 4 units at this particular site. 4 720 megawatt units, so big baseload site. So pretty important conveyor, but the viscosity had dropped from like 320 to like 170. So big drop in viscosity. So it's obvious that there was a significant top up or an oil change or something was done.
Wrong stuff. Something happened
with the wrong lubricant, and he was having a bad day. And I said, "See, the viscosity's dropped from 320 centistokes to whatever it was." And he said, "Boy, we've been running this plant for 20 years without any centistokes, and we sure as hell don't need any now."
I like that one. Without any sense.
So there was a lot of resistance to change, but nevertheless, I had seen enough evidence that we could not only find problems with machines, but we could also understand the underlying root causes, which later led to development of a course that I call FLAB. Okay. Which I'll talk about that a little bit later, so that we can avoid the problems from happening in the first place. So I was really convinced, and I thought, wow, this is just revolutionary. This makes so much sense. I was thinking, in 5 years, everyone will have adopted it. Yeah. And I'm going to have to figure out something,
kind of the next iteration,
a new deal for my career. So, but turn the clock up 30 years and still see the same mistakes being made in the same way on the same types of equipment. So
we've been slow on the uptake.
Yeah, I have some theories for that, and I'm now in a position where I think I can change that within the organization. Yeah, and I've developed some approaches for communicating things in a different way. So,
do you agree? We usually say, like, of course, we specialize in lubrication, right?
Right.
And I tell everyone, lubrication isn't inherently difficult.
No.
Now, what makes it difficult is doing it the right way for an extended amount of time and making sure that everyone's on the same page. It's more behavioral than it is anything else. Do you feel like that's a good analog for just kind of reliability and maintenance as a whole as well?
Yeah, it's cultural.
Yeah.
We have deeply seated cultures that are reactive in nature. And to be honest, being proactive runs a little bit counter to human behavior. We tend to be a little bit reactive in nature. But I think systemically within organizations, we sort of set ourselves up to fail. I can recall many years ago, So as you well know, I was a co-founder of Noria and was with Noria for a long time. And just lubrication ran its course for me. I'd done all that I wanted to do in lubrication. But there was a period of time when I was working with one of the big automotive manufacturing plants. And actually, big company. It was multiple plants.
Okay.
And it was at a time when automobiles were beginning to utilize much more sophisticated, large, molded plastic parts like dashboards and things of that nature.
Yeah.
So the machines that make those are called injection molding machines.
Correct.
These are very intricate parts. So you look at cars in the 80s versus cars in the 90s and then on, and rattles and squeaks started to diminish quite substantially, largely because of these sophisticated molded parts. But the machines to mold these were very, very high pressure servo hydraulic machines. They were having all kinds of problems with them. So I was asked to come in and look at it. And the problem, of course, was they had excessively contaminated fluid. It was causing servo valves.
Hydraulics, of course, very sensitive.
Yeah, and also these were 4,000-ton presses.
Yeah, very high pressure.
Yeah, and putting a lot of energy out, and you had swash plate variable volume axial piston pumps, and very sensitive to contamination. So that was their problem. So we cleaned up the contaminant, with breathers like the ones behind me and filters like you've got some laying around here. So we just cleaned up the oil and the problems went away. Said, great, now train all of our guys. So I was doing a workshop on contamination control for a bunch of automotive millwrights. And thinking I was 29 maybe, young guy. These guys were, 50s and a lot bigger than me. I was a real shrimp back then. And these guys were angry. They did not like me one bit. Did not like me
Felt
one
like
bit.
You were telling them how to do their job.
No,
or
that wasn't it at all.
No? Okay.
No. They were mean. I actually felt physically threatened in that training environment. The only time I'd ever felt that. And during a break, a master millwright, so that's going to be your top artisan, your top craftsperson, walks up to me and he apologized collectively for the group. And he said, Drew, sorry about them. They don't dislike you. They know what you're saying is correct. They know it. And I said, then what's the problem? I said, well, you're talking about taking away their fishing boats, their hunting cabins, and things of that nature.
The overtime that came with the failure?
I said, I haven't said anything about hunting and fishing. He said, yeah, but 30% of their pay comes from overtime. So we're asking for reliability, but we're rewarding failure.
That's right.
I mean, you think about this, that's an extrinsic reward.
Yep.
You think about this within the intrinsic realm. And, sometimes when things fail, the guys who are on call out, they have to go in and fix it. So,
That's right.
A team's on call out. So at a plant, engineers, for instance, they rotate. You've got this call-out weekend, and these crews have these call-out shifts. And so the crew has to come in and get the plant up and running again, fix the machine. And the next week, the general manager or the engineering manager will invariably seek out those guys, pat them on the back, attaboys, right? Yeah. So we're intrinsically rewarding behaviors that are reactive in nature.
Yes.
When was the last time you saw a GM go intentionally give an attaboy to a lube tech for running a good grease route? It just doesn't happen. Which of those is more important in terms of driving value?
Of course, the good lube route, all of this, right?
Absolutely.
Proactive maintenance, the failure avoidance is sedentary. It's one of those aspects that it's boring. And unfortunately, you're right. I mean, there is the behavioral aspect of this that you do get the attaboys. And I don't know that I've ever seen anyone celebrate a non-event, right? Because you never know when the non-event was going to take place.
You just never know. Yeah, you never know. So It's culturally challenging. And I recognized this many years ago. And so I developed actually a workshop. And for a number of years, I was doing kind of coat and tie.
Okay.
Coat and tie consulting.
Stuff.
Yeah. And it was called Plant Reliability in Dollars and Cents.
Okay.
So it was the economics of, why you should do that. I still do that work today. In fact, I train all of our senior leaders on the plant reliability in dollars and cents. In fact, I just delivered a session in Australia last week. I just got back from Australia. And I did that for a number of years, and I would help my clients to figure out what's it worth. Where are you right now? Okay, you're at the 32nd percentile.
Gotcha.
What's it worth to you to get to the 80th percentile? What's it going to cost you to get there? And then you can start creating a cost-benefit analysis. And the reason I developed it was that reliability was viewed as a synonym for maintenance. And at the upper echelons of most corporations, where you've got a lot of lawyers, accountants in the C-level positions, they view maintenance as a cost center.
Right.
So I presented it as a value center. I have enhanced that message beyond just profitability through improving uptime, reducing cost, to include safety.
Yeah.
So this is well documented. A reactive maintenance event is 4 to 5 times more likely to produce
a reportable
or an injury or an adverse health or safety effect than is a planned event, because you may not have enough time, you may not have good understanding of the problem, you may not have the right people, the right parts, the right tools, the right pre-work. All of this stuff contributes. You could be under time pressure. All of this stuff contributes to unsafe operations. Well, when I was doing this, this kind of coat and tie work, I remember walking through a plant with reliability engineers, and I still had, I was still pretty comfortable around the machines.
You're right.
And I'm with these reliability engineers, and I'm pointing out things all over the place that are problems. And it wasn't showing up in their vision. They wasn't showing up in their viewpoint. They didn't know what to look for. And I thought, God, I wish I could, train them on lubrication, alignment, and balance, and fastening, and all these first principles. The problem is most reliability engineers don't have the time to go to 3 or 12 3-day classes to get everything that they need. So I thought, well, something, I think I can consolidate this into an awareness training program
so at least
for these reliability. They have an awareness.
Yeah.
So I created this course, Proactive and Precision Maintenance, with a focus on flab, fasteners, lubrication, alignment, and balance. So you spend 3 days on lubrication. I spend 3 hours on it.
Gotcha.
Right? So, and if they want more on lubrication, I say, just go to an ORIA class, right? So I cover everything, a little bit of the dollars and cents. I give them a little bit in terms of the physics of failure, mechanical and electrical failure mechanisms.
Gotcha.
All right. If you don't understand mechanisms, mode is what's going wrong.
Yep.
Cause is why it's going wrong. Mechanism is how it's going wrong. If you don't understand the mechanisms, you can't get from mode to cause. A little bit on reliability engineering basics, some of the mathematical concepts and root cause analysis and FMEAs and those kinds of things. A good overview on condition monitoring, all the different technologies that we utilize, not training, awareness, how they're used, so on and so forth, and then a deep dive into fasteners, threaded fasteners, welded fasteners. I deal with leak detection and repair, which occurs at fastening points. I deal with belt tension,
slippage or something.
Yeah, electrical fastening. So 50% of what goes wrong with electrical systems It's fastening. It's, whether it's cable to connector, connector to terminal, bus bars, whatever it is, it's an electrical connection. So everything related to fasteners. Little introduction to lubrication with a heavy emphasis on contamination control and good application and management of having the right lubricant, right quantity, right time, all the rights of lubrication.
How much? So with the flab, everything that we're talking about, if you were able to address all of these issues, is that 80% of failures that you'd expect to find in your plans? At 90%? I mean, in your experience, what do you typically see?
So because flab, I deal with both electrical and mechanical mechanisms. So electrical alignment would be, for instance, harmonics. The increased use of variable frequency drives produces a lot of harmonics. It's reactive power. So it's nonlinear loads. And harmonics are multiples of in the U.S., 60 hertz, and other countries, 50 hertz, creates problems. Balance, phase-to-phase, voltage, current, inductive, resistive balance. So I deal with everything. But if you apply what's taught in these classes, except for misoperation, I think you're probably covering 80-90% of all of your failure modes, because it's very much focused on first principles. Now, again, they attend this 3-day class, and I think I've taught 2,500 just at Anglo American.
Okay.
Yeah, people.
Right.
And they attend this class, and as an engineer, now you at least have awareness of the things that you need to be looking for.
It doesn't make you a master. You got to do that on your own. You got to seek another avenue to get that done.
Well, generally, so as an engineer, I would have a technician that I get trained further on, say, precision alignment. I would have a technician that I have trained on vibration analysis. I would have a technician that I would have trained on lubrication. But as the engineer, my job is to understand everything that they're doing, run out front, set the goals, and clear any hurdles that they encounter. And so the course really was designed for engineers. Now, I have a lot of supervisors and artisans that attend the class, but that's who it was designed for, to give that person the overview of the entire field so that they can do their job.
Yeah.
It's, as a young engineer, it's difficult. What I've done is I've just tried to pack 34 years of experience into one class.
Of course. So unfortunately, we're kind of running low on time here, but I want to make sure that you get the last word here. So if you were to give anyone, and this is great because you're talking about packing all of your experience into a course or something. Yeah. So let's say that we've got a young reliability engineer, someone that's just kind of getting into the space. Words of wisdom for them, what would you say? Yeah, so learn everything that you can. Try to prioritize, where you put your effort, and really do understand the value proposition to the organization. Reliability is not a goal. Reliability is an enabler. There you go. The goal is improving uptime or profitability, reducing cost, driving safety. Don't forget the safety aspects of reliability. Reliable assets are safe assets. Another thing that I would suggest is that you really get yourself up to speed on the energy aspects of reliability. The U.S. Department of Energy has done a number of bandwidth studies on the opportunity to reduce energy consumption in industrial settings. So for the mining industry, it's about 21%. It's actually a little bit higher in a chemical plant. I think it's 23% because of all the heat that's utilized in that industry. And that 21% is, a couple things. Number one, that energy savings goes straight to the bottom line. Sure. All right. Does not pass through cost of goods sold. Number two, that's a 21% reduction in your carbon footprint. Everyone is interested in reducing their carbon footprint. Number three, it's reducing wear and tear on your equipment. You think about your job as an engineer, and it's this. It is to convert energy from one form to another, effectively and efficiently,
and transfer that energy along intended pathways with no deviations or minimum deviations to the point at which work is done, whether it's a pumping, conveying, crushing, whatever the case may be.
Mm-hmm.
So our job is really to manage that energy flow.
And I can see how flab very much, because you unintentionally create heat out of the energy where it should be doing something mechanical that we want it to.
Absolutely. Flab is all about that. So your energy losses, are parasitic friction associated with poor lubrication, misalignment, unbalance, mechanical looseness. We have losses at leak points, which again are flab issues. For instance, if your belts aren't tensioned correctly, I did some belt studies and we had belt slip, and I'm talking about V-belts. We have a lot of belt-driven equipment in the mining industry. V-belts with as much as 16% slip.
So that's a huge energy draw that's not actually getting put into its usable form, what it needs to be doing.
Yeah, and it's reducing our productive throughput. So
it cuts two ways.
Flab is very much about, I didn't think about it when I initially created the class, but it's very much about managing those energy pathways. And we all have pressure to deliver sustainability to our shareholders. And the pressure's not going away.
Right.
Most big companies have net zero by goals. Ours is 2040, some are 2050, but our carbon footprint needs to be negated to zero. That's our commitment by that point in time. 21% doesn't solve the problem, but there is no silver bullet here.
Right.
There's no one thing. But we can make a contribution that not only reduces our carbon footprint, our energy bill, but also makes our machines last longer and makes our machines safer. Those belts that are slipping, sometimes they catch fire.
That's right.
Yeah. So, focus, make sure if you're a young engineer, make sure that you have a very clear plan. And then the last thing I will say is reliability does not occur behind your computer screen.
Get out there on the plant floor, get to the equipment.
What Toyota says, go to Gemba, the place at which work is done. I sometimes ask my guys how much time that I spent on my computer when I was a young engineer. And they say, we're not really sure. They don't think about the fact that, no, we didn't have computers back then. So what we did was we went to where the work was. Right. And I encourage, in fact, I have set up for my teams what I call work of the role standards. And I've identified what percentage of their week needs to be doing this, and this. I don't think you can be an effective reliability engineer or maintenance engineer if you are a section mechanical engineer or electrical engineer unless you're spending 30%. And you need to be asking questions. As a reliability engineer, your job is to find, understand, and solve problems. It's the supervisors. It's the artisans, the skilled trades. They know what's going wrong. They usually know why it's going wrong. If you open up your ears. Yeah. God gave you one mouth and 2 ears. Use them in that proportion.
That's right.
So that would be those would be my tips. Understand your goals and why you exist for the organization, and get into the plan.
I think that's fantastic. How would people get in touch with you?
You can go to LinkedIn. I'm on LinkedIn. Reach out to me there. My email, it's kind of a long one, but it's drew.troyer@angloamerican.com, one word, angloamerican.com. Happy to email me as well.
Well, very much appreciate you stopping by. And
thanks, Wes.
Sounds like we got a lot to unpack, so maybe get you back here for another one, part 2 or something.
That'd be great. Thank you.
All right.
Appreciate it.
And for everyone joining us, thank you so much for another Gear Talk. Always like and subscribe. If you have any questions, comments, or topics that you'd like featured on future Gear Talks, you can always reach us at podcast@noria.com. Thank you, and we'll catch you on the next episode.